Uh, okay, yeah, this is me, Muhammad Al-Ghazali Musa. I'm a student in the Department of Meteorological Engineering, taking a master class. Uh, so, within the course of advanced material characterization, I present a topic about SuperAlloy characterization using laser-induced breakdown spectroscopy and micro-XRF, which is one of the interesting topics. One of the new kind of new or non-common technology for characterization. Most of the people that hear about XRF, the normal XRF in millimeter focus, but how about the micrometer focus and how about its resolution and its detection limits and etc. And also, what is the laser-induced breakdown spectroscopy and what is function and how it could serve us in the term of Bowden metrology and superalloy. So within this presentation, we'll take a look about this paper, which is titled by Characterization of Elemental Distribution of Superalloy Composite Powders by Macrobeam X-ray Fluorescence and Laser-Induced Breakdown Spectroscopy. We'll have insight generally about this paper and about the topic itself, and after that, we'll move further to know about LIBS and micro-XRF, and we'll see some of the other methods also utilized in this paper. And after that, we'll give some remarks concluding this presentation. So first of all, what is barometrology? And also, what is superalloy? And what is the relation between those two? So for general, okay, so barometrology is like about the manufacturing process, which we are using like mechanical mixing and then mechanical compacting, and after that sintering in order to form a solid components. So this solid components, it's like brick or it could be superalloy in itself. So the superalloy, which is material, has a very good thermal stability, mechanical strength, and corrosion resistant, and also creep resistance at very high temperature, above 600 centigrade. So, as I mentioned, powder metrology is one of the bricks in the superalloy characterization. So, this is the relation between powder metrology and superalloy. In general, in this paper, okay, we are trying to understand the distribution of coupled uh, within the mechanical mixing with the superalloy. So we have coupled and we have like, superalloy. So how about the mechanical mixing and about the time for the grinding? How it's affect the homogeneity of composite in general and how we could detect or measure the performance through the characterization. Of course, surface characterization could be happen with different equipment. But how about the range of detection? How about the resolution of it? And also, how about the depth profiling? How we could do depth profiling using such equipment? So here is the main part of the topic. So interestingly, okay, we could do depth profiling through laser ion breakdown spectrometry in order to determine the composition uniformity and even the distribution or the distribution like in a term of diffusion. And then also we could know about the migration of different powder during the mechanical mixing. So in general, we are using a synergetic way between micro-XRF and laser ion laser-induced breakdown spectroscopy for analyzing the surface composition distribution and also by the depth profiling to measure the effectiveness of the mechanical mixing among different grinding times. So what is the laser-induced breakdown spectroscopy? So laser-induced breakdown spectroscopy, we are using here a very high laser plus in order to blend the surface. Of course, it will distract like some of the layers, but the rate of ventilation or even like the domain of ventilation is too small because it's micro focus. And after that, it will form a plasma. So, and then the emitted light from the excited atoms will be analyzed and will be like as fingerprints for the metal composition. So it has many merits. So from its merits, it's real-time characterization. So instantly you will know about the composition of this material of this sample. So, and moreover, the rate or like the limit of detection, it's so what you can say, it's in very low, okay? And also it has like ability for detecting like very sensitive elements, maybe hydrogen, lithium, also boron, okay? So, and sample preparation here is so easy as you are just like you need to create pellets, okay? And after that, you need to insert the pellets in the sample place. So also there are some portable devices. You could use them in a field without need like to carrying sample and come to the lab, yeah, for geological detection and etc. And also microscale spatial resolution with high sensitivity, as I already introduced. Maybe for example, if you want to compare this method with XRF, XRF like it's not giving like that accuracy in a term of VVM measurement. Yeah, so XRF is being like more reliable when we are talking about percent in a concentration, so around like more than 1%. But when we are decreasing from this 10,000 VVM, so how is the accuracy of XRF? So most of the researchers, most of the scholars, most of the practitioners, they are not agreeing about using XRF in such like low detection or low concentrations. So here it's more reliable for it. Depth profiling, it's about craters, which we will discover it later. So and also it's enable like compositional imaging of complex materials. So the second device is a micro X-ray fluorescence. What is a micro X-ray fluorescence? Micro X-ray fluorescence is also like using focused X-ray beam to excite like atoms in the sample. But here we are using like micro focus. In the normal XRF, we are using like millimeter focus. So which is like a wide bigger. Okay. So here the emitted characteristic X-ray fluorescence, it will be detected, and after that we will identify and quantify it in order to know about the element. Like through the intensity, we'll know about the element concentration. So what are the main pros of this method, okay, or of this device? It's providing like, two-dimensional elemental mapping. And after that, it's very effective, like, for detecting elemental distribution and segregation. And also the depth ventilation, yeah, it's typically like shallow, but when we integrate it with LIBS, it will give like a powerful technique for depth profiling. Like imagine you will have like 2D area, and after this 2D area within it, like you will dig deeper in order to know about the composition under that surface. So this synergetic way or this complementary way, it's very unique and very powerful. So micro-XRF provides like broad area surface mapping, while LIBS offers depth profiling. So, for example, if we have like say elemental composition and this composition is not uniform, and we want to know about uniformity, like as we are trying like to create maybe like aircraft alloys. So we need to ensure the uniformity of the composition of it elements. Yeah, right. So how we could characterize it? So is it necessary like yeah to break down it to digest it and after that analyze it with the well-known like destructive chemical methods? Of course not. So we need okay other methods also like some people that are using like SIM-ADS. Okay, so SIM-ADS, but it's just like characterizing the surface. So the thing is like this, we need a unique method that without even like slicing the material uh, to tell us about the composition. Okay, so uniformity of the composition in many applications is so mandatory. As we are seeing here, there are like three type of materials with different uniformity. So of course, the first one, if you want to like detect in down or like in depth, it could be different than the other one. So we could not use the same method for all of them. So we need like, depth profiling in order to identify the layers distribution or the layers homogeneity. Okay, so this is the main benefit for this energetic way using like micro-XRF and the depth profiling LIBS. So this is the main difference between the SIM ADS and this method. Like SIM ADS, we need to slice, but in our method or in this paper method, like we don't need like to slice it. So as we are increasing the lateral of the pulse, so we are digging deeper. So okay, how about the initial material composition? So the composition is mainly from two components. The first one is a superalloy, and the superalloy containing like different material or different like elements, nickel, chrome, aluminum, till like thallium with a different concentration, but the most dominant one is nickel, more than 50%. So their size distribution is the average size distribution is 100 micrometer. And we are trying like to mix them with copper. So the average size distribution of copper is 5 micrometer. So on the left hand side, we are seeing here the morphology stem. Like yeah, morphology stem. We are here seeing the uniformity of the size distribution, and the figure B on the app line is telling also about the crystality, crystality information about SuperAlloy. So it's clear here, it's like one alloy based and without like, any other ingredients contained. And in order like, to set it as a baseline. So later when we are doing the mechanical mixing and we are taking a sample during different intervals, there we will detect, okay, the change in this composition. So how about like alpha cobalt and how about like beta cobalt? Will it be integrated like partial or total or how? Okay, this is the thing like we wanna characterize and wanna know. About the cobalt here, as we are seeing, it has like like filamentous morphology, something like this. So for doing the test or the mechanical mixing through the mills, we or the paper used like the authors in this paper they used like 8 grams of couple with 42 grams of superalloy to create 50 gram sample, and they added like around 100 gram of steel balls, and they repeated or they rotate the mill with 200 revolution per minute. And after that, they took samples during several intervals from 30 minutes till they reached like 1 day completely, 24 hours. So as we are seeing here from this graph, it's like showing us about the gradial distribution or the gradial uniformity of the couple. As we are seeing in the first one, so the size distribution was unhomogeneous and it wasn't like let's say not normal like because like in a histogram on the right side, so after 30 minutes of grinding, most of the cobalt they are concentrating in a different places. It's kind of like yeah, um, an abnormal like distribution, and after that it moving till at D here after 8 hours. It's like trying to give like homogeneous distribution around 60 65 percent, okay, for more than like 35 from the couple, or more than 35 from the area or the stamp area. And after that, it moving till it's like reach here to the normal distribution curve. So it's generally it's concentrating around 60% of a cover in the surface for more than 50%. So it's considered like a very good result for the mechanical mixing. So from here, we could give like um, a remark. So mechanical mixing, it is started well. It started in a wall mixing way, and after that, it moved sequentially till it reached like 24 hours. It distributed the coupled in a very good homogeneous way. So time is considered crucial in terms of mechanical mixing, as more time give it like mechanical mixing or to the mill, it will give uh, more uniform composite. Yeah. So the other thing, firstly, characterization in this domain, and actually, yeah, it's like this. It's a 2D domain. So the scanning, it's 4 by 2 millimeter or 4 by 2, yeah, millimeter. So it's a very wide area actually for detection. So okay, also like for confirming about the homogeneity of the created pellets. Here, they are like SIM AS MX. They are showing us about the uniformity of um, the created billets during different times for the mechanical mixing. So as we are seeing firstly, the cobalt was in like, yeah, that much concentration, but after that it really moved to be uniform and to be fixed like, in a uh, certain concentration in the detected surface. So also like XORD, it has been collected or it has been collected. So we are seeing here among different XRD spectra after 25 hours till 25 hours, there are integration of alpha cobalt and eta cobalt, in the main SuperAlloy. So it's giving us a clear evidence about the effectiveness of the mechanical mixing among different time for grinding, on different times for grinding. So, and after that is the stage, for the laser induced breakdown spectroscopy. So, as we are seeing here in the left photo, uh, in all it's given like the distance, millimeter. It's like an area. So, and inside this area, there's like a detection depth. So as more plus, more like more appellation for a surface and more penetration. So here we are seeing different craters. So uh, craters, appellation, more pulses. It means more penetration or uh, in-depth penetration. So here in this example, the penetration is still 8.1 in a minus as we are looking here in the back. So yeah, this method it's giving depth profiling till minus 8.1. We could increase it, so we're just increasing the pulse rate, okay? And after that, on the right hand side, we are seeing two compositional images. They are telling us about the metal composition among two grinding times. The first being after 4 hours and the second after 24 hours. So clearly we are noticing from the surface and we are getting in depth the concentration of copper is changing. While other concentrations in down like as titanium, aluminum, tungsten, they are like almost remaining same. Also, Chromium, it has like, yeah, different size distribution. So, as in the surface, almost we could say around zero, but after that, when we are digging inside, it's appearing to be high. Similarly, also about the cobalt. Cobalt initially on the surface, it's considerably high, and after that, it is decreasing among the time internally. So this is showing us about the effectiveness of this method for reliable mechanical mixing. And as we are giving more time for grinding, as we are ensuring homogeneity in term of composition. So yeah, this a short presentation about this powerful technique for domain, spatial, and in-depth profiling. So by this, you will have like 3D characterization. So right, the depth profiling here is around 8.1 micrometer, but you could increase it by increasing pulse. And also, this method we could say it's non-destructive system, even by like because like some will ask, okay, so it will apply to surface, so it will remove some of the layers, create plasma. But yeah, you imagine like the induced beam or the induced or the emitted ions, which it will be like a fingerprint for the characterization. But the things like this, it's micro focus, so it will just this track like very, very, very unwieldy, you could say like, a teeny domain, within this, within those layers. So it's a very powerful method. Detection limit is too low, high resolution, and also full characterization. And even for some of the methods, they could not measure like some of the elements as lithium, lithium, etc. So this method could be able, to measure those sensitive elements within the periodic table. Yeah. So this is the last, and then they are like the references and the sources where I grouped or created the presentation from them. Thank you very much for watching. I hope I gave like an insights about this method. And thank you once again.